So this is a three-part walkthrough on the Black Scholes Merton pricing model. So the reason why we've segregated this into three parts is that the first part will cover the basics of the underlying concepts which ride on to the Black Scholes model. The second part is a little more mathematical, but it's not too mathematical because I didn't want to crowd out the underlying concepts with too much of mathematical equations, which will then build on to the part three, where we'll analyze a couple of questions and problems revolving around the Black Scholes model. So this three-part presentation, as in the case of the other walkthroughs which have been loaded on this channel, ride on the book on options and derivatives by John Hull. And for those who want to get more knowledge and expertise on the mathematical aspects of the Black-Scholes Merton model, can have a look at the chapter in John Hull's book where it's very well explained. Now let's start with the basics. So you take a stock whose price today is S, and there's a short period of time which is delta t. So the return on the stock is assumed to be normally distributed. So delta S, which is change in the stock, by S, which is the original price, it tends to a normal distribution, which is defined by phi of mu times delta t, comma sigma square delta t, where sigma is the standard deviation. So variance becomes sigma square, and sigma also is a measure of the volatility, with mu being the expected return. Now, one important aspect which you need to keep in mind is the log normal property, which is something which we'll be looking at various points in time in this walkthrough. So the log normal of ST minus log normal of S0, which is the initial price, is given by this normal distribution, which is mu minus sigma square by 2 times t, which is the time to maturity, comma sigma square t. So as you all know that a normal distribution can be defined by its mean and standard deviation. So if you bring S0 to the right hand side, so log normal of ST tends to a normal distribution phi of log normal S0 plus mu minus sigma square by 2 times t, comma sigma square t. So since ST, log normal of ST is normally distributed, ST2 is assumed to be log normally distributed. Now let's take an example. You have an option or an asset whose initial price is $40 and the expected return, which is mu, is 16% per annum. Please keep in mind that the returns are measured in per annum. Likewise, the volatility also per annum, which in this example is 20%. Now, what is the probability distribution over 6 months? So, from the previous slide, we know that log normal of ST tends to phi of log normal of S0 plus mu minus sigma square by 2 times t, comma sigma square t. So, S0 euro is 40, mu is 0.16, sigma is 0.2, and t is zero point 0.5 because it's 6 months. So from plugging these numbers into the equation, so you get log normal of ST tends to phi of 3.759, which is the mean, and 0.02, which is the standard deviation. Now, for a 95% confidence level, it's equal to 1.96 standard deviation. So, sigma is equal to square root of 0.202. That's what we've calculated in this equation, so which comes to 0.14. So with the 95% confidence, you can say that the stock price or whatever price which you're measuring over the 6 month, it could also be a currency or it could be a commodity, would lie between mu plus 1.96 of sigma and mu minus 1.96 of sigma. So that gives you a range of 32.6 and 56.45. Remember, you have to bring it down to the exponential form. This because the earlier values are a logarithmic value. So you get exponential of mu plus 1.96 of sigma and e raised to the power of mu minus 1.96 times sigma. So that gives you the value of 32.6 and 56.45. So what does this mean? It says that with a 95% confidence, the price of this asset would range between 32.6 and 56.45. Now, what is the log normal distribution? A log normal distribution tends to be skewed to the right. So you can they have only positive values, which can range from 0 to plus infinity. And the expected value of the price, E of ST, is given by S0 times E raised to the power of mu t. E is of the exponential. Remember, the value of E is 2.718. In case you're doing any calculation in any question where you don't have Excel, so you cannot use the exponential function over there. So for that sake, remember that E is 2.718. And similarly, the variance of ST is given by S0 square E raised to the power of 2 times mu t parenthesis e raised to the power of sigma square t minus 1. So these formulas you can remember. I'm not getting into the derivation of how we arrived at, but by themselves, these equations are important for you to solve certain problems. Now, let's take an example of where you can use these equations. So you have as 0, $20, mean is 20% per annum, and volatility is 40% per annum. So how do you calculate E of ST? You know E of ST is as 0 times E raised to the power of mu t. So that's 20 times exponential of 0.2, which is the value of the mean, times 1. T is 1, so it's for 1 year. So which gives you a 24.42. Similarly, the variance of ST can be calculated by S0 square E raised to the power of 2 mu t times e raised to the power of sigma square t minus 1. So that gives you a value of 103.52. So remember, this is the variance. So to calculate the standard deviation, take a square root of this value. So square root of 103.52 gives you a standard deviation of 10.17 per year. Now, typically returns are computed using continuously compounded feature. So ST is given by S0 times e raised to the power of xt. So if you take the log of both sides of this equation, so basically you get ST by S0 is equal to e raised to the power of xt. So which gives you a x equal to 1 by t log normal of ST by S0. So mean, as we have seen in the earlier slide, is mu minus sigma square by 2, and standard deviation is sigma square by t. Now, expected value of a stock price is S0 times e raised to the power of mu t. And remember one thing, expected return is not mu, it is always mu minus sigma square by 2, which is what we've seen in the earlier equations which we have reviewed. And why is that so? Because log normal of expected price of ST by S0 and expected price of log normal ST by S0 are not the same. So mu is the expected return in a very short time, delta t, expressed with compounding frequency of delta t. And mu minus sigma square by 2 is the expected return over a long period of time with continuous compounding. Now let's take an example. Stock with an expected return of 17% and volatility of 20% per annum. So mean is mu minus sigma square by 2, which is 0.17 minus 0.2 raised to the power of 2 by 2, which gives you 15% per annum. Standard deviation over 3 years will be square root of sigma mu times, sigma square by t. So it will be zero point 0.2 square, which is zero point 0.2 raised to the power of 2 by 3, which gives you 11.55% per annum. So again, like in the earlier case with the 95% confidence, you can say that the average return over 3 years can be between 15% plus 1.96 times 11.55 and 15% minus 1.96 times 11.55, or it could be minus 7.64%. Sorry, the dollar should be read as percent, and 37.6%. Now, one very important aspect you need to keep in mind is how do you use geometric mean and arithmetic mean. And that's best understood if you take an example. So let's take the case of a mutual fund, which is giving you returns over a 5 year period of 15%, 20%, 30%, minus 20%, and 25%. Now, how do you calculate the arithmetic mean? Simply add that up and divide it by 5. And you could say that, the fund is returning, giving you a return of 14%. But is that correct? Not really, because you've got certain blips in the middle. So return should actually be calculated using geometric mean, which works out to 12.4%. Now, how does that come? So 100, let's say, is the initial price. So first year your return is 15%. So that you end up with $115. Then your next year return is 20%. So you end up with $138. And so on and so forth. And finally you turn up with $179.4. Now, assuming that you end up with $179.4 at the end of 5 years, at what rate would this be compounded, which is $100 be compounded to give you 179.4? And that gives you a rate of 12.4%. You can always use the geomean function, which is there in Excel, to calculate the geometric mean. But primarily the intent of this quick example was to give you a flavor that it may not be necessarily correct if you take a simple average and say that's the return which a particular asset has given you over a period of time, which could be in years. You need to quantify that in geometric mean terms, because geometric mean, as you know from your earlier high school readings, is always less than the arithmetic mean. Now, what's the other important aspect which you need to understand? That is volatility. And that is nothing but the standard deviation compounded rate of return in 1 year. Now, standard deviation of the return in a short period of time, delta t, is given by sigma times square root of delta t. Keep this formula in mind. So, the stock price is $50 and volatility is 25% per year. What is the standard deviation of the price change in 1 day? How do you do this? So sigma, is 25% per annum or 0.25. 1 day is 1 divided by 250, because it is assumed that there are 250 trading days in a year, or some people assume 252 also. So that gives you 0.004 year. So for 1 day, standard deviation would be 0.25 times square root of 0.004, which gives you 1.58%. So one standard deviation move in stock price over 1 day basically is $50 multiplied by 1.58%, which is 79 cents. Now, how do you estimate volatility? Estimating volatility is done from historical data. So you take observations S0 up to Sn over a period of time. It could be years, it could be months, it could be days. In this particular case, it says tau years. It could be weeks as well. And then you calculate the continuously compounded return in each interval. So ui is given as log normal of si by si minus 1. So si is today's price and si minus 1 is the previous days or the previous months or the previous weeks, depending upon the periodicity which you're using for calculation. Likewise, the standard deviation is square root of 1 by n minus 1 ui minus u bar square. So u bar is the mean and ui is the observation for which you're calculating the deviation. So historical volatility estimate is given by S, which you calculate as standard deviation divided by square root of tau. So volatility per annum is volatility times number of trading days per annum. Now, what is the nature of volatility? It's usually much greater when the market is open. So when the market is closed, obviously you cannot have any volatility because there is no trading happening either on the option or on the stock or any other asset. So that's why we typically measure volatility using trading days. And it's assumed that 252 trading days are there in 1 year for most assets. So life of an option, for example, is number of days to maturity divided by 252. So let's take an example. Suppose it is April 1st and an option lasts to April 30th. Number of trading days remaining is 30 calendar days or 22 trading days. So the time to maturity would be 22 divided by 252, which is 0.0873 years. Now, how do we do this calculation for the standard deviation? So this is the example which I've taken from John Hull's book, and you can see these observations for 20 days, and he's got a stock price of some stock which he has used. And what you need to do is you need to calculate log normal of SI by SI minus 1, which is the last column. So it is log normal of 20.1 divided by 20, which gives you 0.00499. Likewise, copy that formula all the way down and you get the log normal returns for the period. And then you could, using this particular function, you can use the standard stdev function on Excel for calculating the log normal based on the log normal returns, and you get a value of 1.21% per day. So on an annual basis, it will be sigma times square root of T. So which means 1.21% times square root of 252, assuming 252 trading days, which gives you 19.2% per annum. So this kind of brings us to an end of part one of this presentation. So we'll move on in a short while. So part two will be uploaded separately. Thank you.